We're going to look at some different types of formulae now that we need to be familiar with at A-level chemistry. We're going to look at non-metal structures and how we write those formulae. So chemical formulae tell us how many of each kind of atom make up a substance. You might remember from GCSE that some elements are diatomic, they go around in pairs. The list is here. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine and iodine. You might just know that or remember it from where they are in the periodic table. So hydrogen is up by itself, and then it sort of forms like a number 7 on your periodic table. If you see where nitrogen is, you then go across nitrogen, oxygen and fluorine, and then it's all of group 7. Okay, so those are the diatomic ones, or some people remember have no fear of ice cold beer as a way to remember those. Some substances are polyatomic, so there are some quite common substances in chemistry where the molecules have a number of atoms in them. You might recognize some of these or all of these. So carbon dioxide is one example. So each molecule has 1 carbon and 2 oxygens covalently bonded together. Methane, CH4, ammonia is NH3, and obviously water is H2O. So let's look at a slightly bigger molecule, glucose. You can see the structure of it there on the left hand side. It's got, each molecule has 6 carbons, 12 hydrogens if you added all those hydrogens up, and it has 6 oxygens altogether. So the formula, we haven't really said what type of formula, but the molecular formula is C6H12O6, because the definition of molecular formula is the actual number of atoms of each element in, it says there, in a compound. More specifically, is the actual number of atoms of each element in 1 molecule of a compound. Okay, so each molecule of glucose has 6 carbons, 12 hydrogens and 6 oxygens. There's other types of formulae which we will look at over the next few slides. So we looked before on the previous slide that glucose has the molecular formula of C6H12O6, because that's the number of each of those atoms in 1 molecule. Sometimes we need to know what's called an empirical formula. The definition of an empirical formula is it's the simplest whole number ratio of atoms of each element in a compound. So if it was C6H12O6 as the molecular formula, we could divide each of those numbers by 6. And we would get down to CH2O. And that's the empirical formula. Definition is the simplest ratio of atoms of each element in a compound. Okay, so let's see if you can do the same thing with these examples. So you've been given a molecular formula. The ethanoic acid one is actually something called a structural formula. But see if you can use that information and simplify them, divide the numbers by a common number to get it down to the lowest, simplest ratio, whole number ratio. So pause the narration, see if you can change those into empirical formula. Okay, so for the first one, hydrogen peroxide, H2O2, could divide everything by 2 and you go down to HO. Ethane, which is C2H6, if you divide that by 2, it goes down to CH3. Right, ethanoic acid, as I said, it's actually been written as what's called a structural formula. It's given us an idea of the structure of the molecule. The molecular formula would be, if I just add those together, it'd be C2H4O2, and you could divide all of that by 2. And that, so C2H4O2 would go down into CH2O. And ethene and alkene, C2H4, divide that by 2, can go down to CH2. Sometimes it's not possible to make it any simpler. So sometimes the molecular formula is the same as the empirical formula. For example, carbon dioxide is CO2. We can't divide that any smaller, and water is H2O. What we can be asked to do is, given some information, normally some information from an experiment, we're asked to work out this thing called empirical formula, because empirical literally means from experimental data, really, okay, or from experiment. So this simplest ratio of atoms of each element is often deduced from experimental data, okay, and we need to learn how we turn this information into an empirical formula. So here's one example. Calculate the empirical formula of a substance that has the following masses of each element. So 2.4 grams of carbon, 0.4 grams of hydrogen, 3.2 grams of oxygen. Set up a column for each element. It can be one column, it can be two, it can be three. Sorry, it can't be one. It'll either be 2, 3, or 4, or more. We start with the masses. The masses can be given as percentages or grams. In this case, they're grams. So I've got 2.4 grams of carbon, 0.4 grams of hydrogen, and 3.2 grams of oxygen. We divide it by its relative atomic mass. The reason is it turns in mass over MR, or mass over atomic mass, gives us something called moles, which you might remember from GCSE, but we'll learn again as we go through this course. So we divide them by their relative atomic masses. So carbon gets divided by 12, hydrogen by 1, oxygen by 16. We get these numbers here: 0.2, 0.4, 0.2. Don't round those numbers too early. If they're not, if they're long numbers, keep them long, at least 3 decimal places. We then need them as whole numbers. So one way of converting them into whole numbers is divide each of those numbers by the smallest number. So in this case, 0.2, 0.4 and 0.2, the smallest number is 0.2. So divide them all by 0.2 and you get 1 to 2 to 1. So the formula is CH2O. Do another example here, where sometimes we have to do something to get them to whole numbers. So sodium, sulphur and oxygen, this time they've said it's percentages by mass, but the method starts exactly the same. You write down those masses, 29.1, 40.5 and 30.4. If it's percent or grams, it doesn't matter, you still just write those numbers. Divide each one by the relative atomic mass. So sodium is 23, sulphur is 32.1, oxygen is 16. You just get those from the periodic table. Here, these numbers aren't whole numbers. Keep them at least, well, 2 decimal places or 3 decimal places. So I've got 1.27, 1.27, 1.9. Divide them by the smallest number. So in this case, 1.27 is the smallest one. You get 1 to 1 to 1.49. Now, a common mistake is people then would round that 1.49 to just 1. You're not allowed to do that. Okay, if it was 0.9999 or 1.0001, okay, you can round that to 1. Because that's just a bit of experimental error. But 1.49, you can't round to 1. You could round it to 1.5. And then, to get it into whole numbers, you multiply all of those numbers by 2. So 1 to 1 to 1.5 times it by 2 becomes 2 to 2 to 3. So the empirical formula is Na2S2O3. Okay, you've got another example here. Same routine as the previous two. So look back at those examples if you need to. Pause the narration, try and answer this question. Okay, so set up 2 columns because it's carbon and oxygen. And they've got a mass of 27.3 and 72.7. First thing to do is to divide those numbers by their relative atomic mass. So carbon is 12, you get 2.275. Don't round those numbers too early. Oxygen is 16, you get 4.54375. The smaller number out of those two is 2.275. So divide them both by 2.275, you get 1 to 1.997. Now 1.997, that's fine, you can round that to 2. So it's a 1 to 2 ratio, therefore the formula is CO2. Okay, another example here. So pause the narration. I'll just say here, they've been a bit clever with the numbers, with the masses. They've said compound Z is known to contain iron and chlorine. The total mass is 2.5, 0.855 grams of it is iron. So you could do a subtraction to work out the mass of chlorine, and then the method's the same as the other examples. So pause the narration and have a go at this one. Okay, so set up 2 columns, iron and chlorine. So iron mass is 0.855, chlorine mass is 2.5 minus 0.855, which is 1.645. Divide them both by the smaller number, which is before we do that, we divide each one by its relative atomic mass. So Fe you divide by 55.8, and Cl you divide by 35.5, and you get those 2 numbers there. We then divide each one of those by the smallest number. So 0.0153 divided by 0.0153 is 1. 0.0463 divided by 0.0153 is 3.03. Again, we can allow for a bit of experimental error. That is 1 to 3. So it means the formula is FeCl3. Common mistake with an exam question is people forget to write the final answer. They get 1 to 3, but then they don't write the answer. So make sure you write the formula. So in this case, FeCl3. Okay, another example here. They've said it's an oxide of aluminium and 53% of it is aluminium. So it means it's going to be some type of aluminium oxide. So your two columns should be aluminium and oxygen. So pause the narration, see if you can work through this one. Okay, so it's aluminium oxide. Aluminium was 53%, which means the oxygen must be the remaining percentage, which is 47. Divide each one of those by the relative atomic mass. So aluminium is 27 from the periodic table, oxygen is 16. Divide each one of those by the smallest number. You get 1 and 1.496. Again, we can't round that to 1, but we could round it to 1.5. So it's 1 to 1.5. Multiply both of those by 2 to get it up to a whole number. So you get 2 to 3, so it's Al2O3. This next one's got 3 elements, but we can use exactly the same method. So pause the narration, try and work through this one. Okay, so this dodgy liquid from an old refrigerator has got carbon, chlorine and fluorine in it. So we've got 3 columns, carbon, chlorine and fluorine. Divide each one by its relative atomic mass. So carbon is 12, chlorine is 35.5, fluorine is 19. So we get those numbers there. Don't round them too early, keep them to at least 2 or 3 decimal places. Divide them by the smallest one. So 0.95 is the smaller one. So you get 1. 0.958 divided by 0.95 is going to be pretty much 1. Fluorine comes out as 3.02. So we can see, allowing for a bit of experimental error, that's 1 to 1 to 3. And don't forget to write the final formula. It's therefore ClF3. If we've got the number 1, we don't put a little 1, we just leave it without any subscript number. Okay, another question. Hydrocarbon. You'll know this from GCSE, and we'll explain it again in another booklet. But hydrocarbon means it contains hydrogen and carbon only. So the 2 columns should be carbon and hydrogen. So pause the narration, have a go at this example. Okay, so the hydrocarbon is carbon and hydrogen. 81.8% is carbon, so the remaining percentage must be hydrogen. Divide them both by their relative atomic masses. So carbon gets divided by 12, hydrogen just gets divided by 1, so it stays the same. Divide them both by the smallest number. You get 1, and you get 2.67. Now this is a common thing that's happened in recent questions. So I've said if it's close to a whole number, like 0.999 or 0.001, you can round it to the whole number. If it's close to to a 0.5, we can just double everything. If you get a 0.333 or a 0.666, that means we need to multiply by 3 to get a whole number. So 1 to 2.67, to turn those into whole numbers, because it's 0.67, that's like 2/3, multiply it by 3. So if you times it by 3, you get 3 to 8. Therefore, the formula is C3H8. Another example, 5 grams of a compound had 1.955 grams of carbon, 0.435 grams of hydrogen, the rest of it's oxygen, so you'll need to do a subtraction to work out the mass of oxygen. So pause the narration and try this one. Okay, so we've got carbon, hydrogen and oxygen. Oxygen, the missing mass was 5 minus 1.955 minus 0.435, so it's 2.61. Divide each one by the atomic mass. So carbon gets divided by 12, hydrogen by 1, oxygen by 16. Divide each one of those by the smallest number, which is 0.163. So we get 1 to 2.67 to 1. We've got this 0.666 again. So we times it by 3. So we get 3 to 8 to 3. So it will be C3H8O3. Another one. This time it's percentages: 52.1 carbon, 13% hydrogen, 34.8% oxygen. So pause the narration and try this one. Okay, so we've got carbon, hydrogen and oxygen. Divide each one by its atomic mass, sorry, its relative atomic mass. So we get 4.34, 13, 2.175. Divide them all by the smallest number, which is 2.175. You get 1.995, 5.977 and 1. So obviously those first two can be rounded up to whole numbers quite easily. So it's 2 to 6 to 1. So the empirical formula is C2H6O. These are the answers, just to double check that you've got them all right. We can be asked to do one extra step to turn the empirical formula into the molecular formula. Remember, the empirical formula is the simplest ratio of atoms of each element in a compound, whereas the molecular formula is the actual number of atoms of each element in one molecule of a compound. So we normally just have to do a simple multiplication up to turn it back into the molecular formula. So we're going to look at an example as how we turn an empirical formula that we've just calculated into a molecular formula. We need to have the MR to be able to do that. So the vast majority of this method is the same as what you've done for empirical formula, and then there's just one last step at the end. So if we talk through this one, a hydrocarbon is known to contain 85.7% biomass of carbon and 14.3% biomass of hydrogen. They've told us that the MR is 56. Calculate the empirical formula and then find the molecular formula. So the empirical formula is exactly the same as what we've just done. So we write down the mass, divide it by its relative atomic mass. So carbon is 85.37 over 12, you get 7.11. Hydrogen is 14.3 over 1, so you get 14.3. Divide both of those numbers by the smallest number and you get a ratio of 1 to 2. So the empirical formula, just like we've done with the previous examples, the empirical formula is CH2. Right, what we now need to see is what we need to do, how much we need to multiply that up to get up to the MR that we're given, in this case 56. So if we work out the MR, if you like, of the empirical formula, so CH2, that adds up to 14. 12 plus 2 lots of 1, that's 14. We need to get it up to 56. So if you do 56 divided by 14, we get the number 4. So we know that we need to multiply it by 4 to get up to 56. So CH2 times 4 turns into C4H8. And if you wanted to check right at the end, just work out the MR of C4H8. So 4 times 12 plus 8 times 1, that adds up to 56. So that is the correct molecular formula. Okay, so here's another example. Part A is exactly the same as what we've done with all the empirical formula questions, and then there's just one extra step for part B. They've given us the MR. So pause the narration, try and work through this slide. I'll talk through the answers once you've had a go. Okay, so compound A contains 12.78% carbon, 2.13% hydrogen, and 85.2% bromine by mass. So just like before, we set up the columns, in this case 3 columns. Divide each one by its relative atomic mass, and we get these numbers: 1.065, 2.13, 1.067. Divide them by the smallest number, so that's 1.065. We get 1 to 2 to 1. So we know the empirical formula is CH2Br, same as what we've done previously. So there's just one last step to do to turn that into the molecular formula. Well, that CH2Br adds up to 93.9, and we need the MR to be 188. So if you did 188 divided by 93.9, again, allowing for maybe a little bit of experimental error, that's twice the size. So we need to multiply it by 2. So if you multiply the empirical formula by 2, we get C2H4Br2. Another example here, similar to the previous one. Remember, hydrocarbon means it just has carbon and hydrogen, so those will be your 2 columns. So work through it, do the empirical formula, and then convert it to molecular formula. Okay, so carbon and hydrogen. You've been given 85.7% mass of carbon, so the hydrogen must be the remaining percentage, which is 14.3. Divide them by their atomic masses, you get 7.14 and 14.3. Divide them both by the smallest number, you get 1 to 2. So the empirical formula is CH2. Okay, so just one sort of extra step to do now. CH2 adds up to 14. Our MR is 84. If you do 84 divided by 14, that's 6 times bigger. So we need to multiply CH2 by 6, and we end up with C6H12. One more example, empirical formula and then molecular formula. So pause the narration and try this one. Okay, so this one is a chloride of sulphur. So the two columns will be sulphur and chlorine. They've told us that 47.4% of it is sulphur, so the remaining percentage must be chlorine, so 52.6. Divide them by their atomic masses, get those from the periodic table. You get 1.477, 1.482. Divide them by the smallest number, we get something very close to 1 to 1. So it's 1 to 1, so it's SCl. That's the empirical formula. That adds up to 67.6, but the molecular formula is 135. Again, we can allow for some sort of some experimental error. 135 divided by 67.6, we get 2. So we need to multiply everything by 2, so we get S2Cl2. Another question here, hydrocarbon. Again, so just carbon and hydrogen. Work out the empirical formula and then turn it into molecular formula. So pause the narration, try this one. Okay, so carbon and hydrogen, you've got the masses there. So the total mass was 1.8, 1.44 of it was carbon, so the remaining mass must have been hydrogen, so 0.36. Divide them by their relative atomic mass. So carbon is 12, hydrogen is 1, we get 0.12 to 0.36. Divide them both by the smallest number, you get 1 to 3, so it's CH3. That adds up to 15, but we know that the MR is 30, which is twice the size, so we double CH3 and we end up with C2H6. Another example here, I know the answer is written, but obviously we want to show the working and check that we can work through it. So pause the narration and check that you can get the right answer. Okay, so a compound has the composition by mass 5% hydrogen, 35% nitrogen, 60% oxygen. Which compound has this composition? So if we work out the empirical formula, hydrogen, nitrogen and oxygen, divide them each one by its relative atomic mass. So we get 5, 2.5, 3.75. Divide them all by the smallest number, which is 2.5. You get 2 to 1 to 1.5. We need to multiply that by 2, so we get 4 to 2 to 3. So we need to find which one of those formulae has an empirical formula of 4 hydrogens, 2 nitrogens and 3 oxygens. Okay, so A is incorrect because that would be 1 to 1 to 3, so that's wrong. Okay, but B, if you group the nitrogens together, you do get 4 to 2 to 3, so that one matches. C is 1 to 1 to 2, so that doesn't match. And D, for the hydrogen would be 3, the nitrogen would be 1, and the oxygen would be 1, so it would be 3 to 1 to 1, so that doesn't match. So the only one that matches is B. Answers are just here, just so you can check what you've done. I mentioned this briefly earlier on in this PowerPoint. There's something called hydrated salts that you might have done at GCSE. Copper sulphate is a common one that you might study at GCSE. So there are two types of solid copper sulphate. White copper sulphate, which is just CuSO4, it's anhydrous, it doesn't have water. And then there's blue copper sulphate, which is hydrated copper sulphate. It's still just solid, but it has water molecules within the structure, which makes it blue, and it happens to have the formula CuSO4.5H2O. So there are 5 waters for every 1 copper sulphate. There's loads of different hydrated salts. So FeSO4, iron sulfate, has 7 waters in it. Other ones might have 4 waters. So it can be an exam question where you've got to work out how many waters are in this formula. Could be 5, could be 7, could be 4, but it's always a whole number. And we use a very similar method to what we've done previously with empirical formula. Okay. So the water of crystallization, the number of waters, can be determined in a practical method and then doing some calculations afterwards. So here's an example. ZnCl2.xH2O. We don't know whether it's got 2 waters in the formula, or 3 or 4 or more. We don't know. So we need to look at the information. When the hydrated salt is heated, the water in the crystals evaporates and leaves just the anhydrous salt, so ZnCl2. We could compare the mass before and after. We would be able to work out the mass of zinc chloride and the mass of water, and then we could set up an empirical formula style answer. So here's practically how we would remove all of the water. A student carries out an experiment to determine the amount of water of crystallization in the formula of another hydrated salt. The student intends to remove the water by heating the hydrated salt. So you'd put your salt in a container, which is called a crucible, above a Bunsen burner and heat it up. So the student adds the hydrated salt to the crucible and weighs the crucible and contents. The student heats the crucible and contents and allows them to cool. The student weighs the crucible and residue. The student's results are shown below. So we've got the mass of the crucible and hydrated salt, the mass of the crucible and the residue after heating, and then we've got the mass of the crucible. So we could use those numbers to work out a few things. So the anhydrous salt, so that is the salt without any water. Well, the mass of the salt without any water is at the end of heating, so 16.26. But that 16.26 includes the mass of the crucible, so we need to take that away. So we do 16.26 minus 14.80, and that would be the mass of the salt, just the anhydrous salt without any waters, so 1.46. The mass of water lost would be the difference between the starting mass before the reaction and the end mass at the end of the reaction. So in this case it's 16.84 minus 16.26, which is 0.58. And then what we do is something very similar to the empirical formula, is we set up 2 columns, but this time it's not for individual atoms. We do it for the anhydrous salt and we do it for the water. So in this case, zinc chloride had a mass of 1.46, the water had a mass of 0.58. Just like we did with empirical formula, we then divide it by the MR. So ZnCl2, zinc chloride, adds up to 136.4. Water adds up to 18. So divide each one of those, 1.46 by 136.4, 0.58 divided by 18, we get the numbers 0.0107 and 0.0322. Just like before, we divide them by the smallest number, we get 1 to 3.01, but it needs to be a whole number. It has to be a whole number of water molecules. So allowing for some experimental error, we would say that x equals 3, so the formula is ZnCl2.3H2O. Right, so we've got a similar type of problem here. Iron 2 sulphate, you can see the formula of iron 2 sulphate is FeSO4. It says it in the brackets there at the end of the question. Is heated, they form 3.04 grams of the anhydrous salt. So we should be able to do a subtraction to work out the mass of water, and we have been given the mass of the iron sulphate, FeSO4. So you might want to pause this explanation a number of times. So I'll give you a bit of time at certain points to pause to carry on. So the first thing you need to do is set up 2 columns, one for the iron sulphate, one for the water, and decide what masses you'd have at the top of those columns. So pause the narration, and if you think you know what you're doing, just do the whole question and you can check it at the end. If you're not sure how to set up those columns, pause the narration, have a go, and I'll show you how it sets up. Okay, so it's iron sulphate and water. The iron sulphate, they've told us the anhydrous, that means without water, the FeSO4 is 3.04 grams. To work out the mass of water, It's the starting mass minus the end mass. So 5.56 minus 3.04 is 2.52. So we've now got the masses. So you might want to pause the narration again, work through the method. It's very similar to what we did previously. Divide them by the MRs, divide by the smallest number, try and get a whole number ratio. Okay, so we divide each one by their MRs. FeSO4 is 151.9, water is always 18, that's 0.02, 0.14. Divide them both by the smallest number, you get 1 to 7. So that's telling us that X is 7. It's a 1 to 7 ratio, so it's FeSO4.7H2O. So X equals 7. Okay, another example here. So pause the narration, see if you can work through this one and calculate X. Okay, so it's 46.1 of the hydrated potassium dichromate, so that's the total mass. 35.3 of it was the anhydrous salt, so the K2Cr2O7, which means the water mass will be the difference between those two masses. So K2Cr2O7 is 35.3, water is 10.8. Divide them both by the MRs. Be careful with the MRs. K2Cr2O7 adds up to 294.2. Water always adds up to 18. So you get 0.12 and 0.6. Divided by the smallest numbers. 0.12 is the smaller number. So you get 1 and you get 5. So it's a 1 to 5 ratio. So X equals 5. This is quite a tricky example. So as I go through this slide, you might want to try and fill in as much as you can, but pause the narration and try and fill it in. And then when you get stuck, hit play again and listen to some more guidance. You will get better at this type of question when we learn some more information throughout the course. So it's a slightly different question. A student carried out an experiment in which 24.96 grams of a hydrated salt was heated until constant mass of 15.95 grams. In this question, they've told us that the formula is XSO4.5H2O, so they've given us the number 5 there. Instead, we've got to work out the identity of the metal ion X, or X2+. So your first job really is to fill in that table, and hopefully that one's not too bad. So you might want to pause the narration and fill in that table. Okay, so the mass of the hydrated salt, in the question it said it was 24.96. The anhydrous salt formed was 15.95. So the mass of water that was removed is the difference between those two numbers, which is 9.01. Okay, still a very, very tricky question. You might have an idea of what you need to do. You could use moles, if you can remember moles from GCSE, and we'll cover that more as we go through this cut through A level. Alternatively, there's a scaffold, there's a step-by-step of what you could do in your notes, or you might have your own idea of what to do. So pause the narration if you've got an idea, have a go, see if it works. If you're not sure, listen to some more instructions and pause a little bit later. So I'll give you some opportunity to have a go now. Okay, so there's a scaffold in your notes, and if you use that step by step, you will get the right answer. Okay, I have used moles instead. You might remember from GCSE that moles is mass over MR. So I could work out the moles of water by doing mass over MR, so 9.01 over 18, which is 0.501. Now if I look in the formula, it's a 1 to 5 ratio. Okay, the moles of water is 0.501, so the moles of XSO4 must be that number divided by 5, which is 0.1. Okay, I could then work out MR. Again, this is learning or remembering some equations to do with moles, and we'll learn all about these in another booklet. But MR, rearranging that equation, MR is mass over moles. So the mass we've already worked out as 15, or we've been given as 15.95. The moles is 0.1, so the MR is 159.5. We now need to take away the MR of SO4 because we're only interested in the X. So SO4 adds up to 96.1. So if you do 159.5, take away 96.1, we end up with 63.4. And then we've got to find the closest match on the periodic table. Obviously, this is experimental data, so it might be slightly different. 63.4, there isn't a 63.4, but the closest match is copper at 63.5. So we would say that X2 plus is Cu2 plus. Okay, one more example. So read through this question, pause the narration, see how far you can get. Okay, so a hydrated salt, compound A, is analysed and has the following percentage composition by mass. Chromium 19.51%, chlorine 39.96%, hydrogen 4.51% and oxygen 36.02%. Calculate the formula of compound A, showing clearly the water of crystallization. So eventually, to get full marks, we need it in the formula format, the anhydrous salt dot XH2O. But before we do that, and again, you might want to pause this at certain points and have a go yourself, I would set up individual columns for chromium, chlorine, hydrogen and oxygen. So you might want to pause the narration and get a ratio for those four, the chromium, chlorine, hydrogen and oxygen. Okay, so if we work through that, divide them all by their atomic masses, we get 0.375 to 1.126 to 2.251. Divide them all by the smallest number. So you get, divide them all by 0.375, you get 1 to 3 to 12 to 6. So the empirical formula is, or the ratio is 1 to 3 to 12 to 6. But remember, we need to put it in the format dot something H2O. Okay, so if I've got 6 oxygens and 12 hydrogens, that must mean I've got 6 waters. Okay, that would give me 12 hydrogens and 6 oxygens. So that's why it's CrCl3 and then 6 H2O.